Diego, who will be talking to us about De Sitter, static patch solipsism. I should add, because I'm not sure it's on the screen yet, Andy Strominger will also be talking more about De Sitter space things on Thursday at 1 o'clock. Should be on the screen soon. And his title is suitably ambiguous as Progress in De Sitter. Because I'm not sure he decided what he's going to talk about yet. Okay, thank you very much, Diego.
Thank you so much for the invitation to come here to this workshop and discuss this work. So I should mention my collaborators, Dionysios Aninos and Sean Harnell. And even though this is not my latest work, it's something that I'm coming back to, so it's a good idea to give a talk whenever you're coming back to something, so you remember what's going on. So this is from a paper I think 3 or 4 months ago. So let me try to explain what I mean by solipsism, the static patch, by making a comparison between two possible observers. So from the point of view of De Sitter, so this is sort of a cartoon of De Sitter. This is square plus, future infinity. So there are at least two natural observers one can consider in De Sitter spacetime. So the first one, which is the one that has been studied the most, is what, let me just write some words and see if it makes sense. So it's what you can call a global meta-observer. So this guy is a guy sitting here at square plus and making doing experiments at square plus. So why do we worry about this observer? There's some very good features about this observer. Sitting at square plus is a natural place to put boundary conditions. So, let me say something else. And because of that, it's sort of a natural place to define some sort of S matrix. Let me just write like that, and it'll become clear in a second why I'm writing like that. So it's sort of what I mean by this, sort of a natural place to try to discuss gauge invariant observables. And this is a little bit by analogy with ADS-CFT. You can think of these things as an analogy to ADS-CFT. So we just found a place where it's natural to put a boundary, and this we're going to define our observables the same way we did in ADS-CFT. Now, there are many other good features about this type of observables. They are connected with real-world physics. If you want to study the past inflationary phase, so past inflationary phase of our universe, we are this sort of observer in some way. When we look at the sky and we look at the CMB, we're looking at the universe from this point of view. And also some other very good feature of this, which is again maybe connected with the story, is that because there's a boundary, there's an asymptotic symmetry group, and there's some conformal group symmetry that we can use to characterize our correlation functions, let's say. So
just a basic clarification. So when you say boundary conditions, you mean you assume some boundary conditions for the scry minus?
You can put it. I mean, you can select the modes that you want. Yes, you can put boundary conditions scry minus too, but you can think of looking at modes here that you're interested. You can just classify the modes by what boundary conditions they have here. Yes, you can add boundary conditions scry minus as well.
I mean, generically, you would need to add both.
Yes, you can turn on some mode or some other mode. I mean, depends on what you're interested in, whether you're interested in fast falling or slow falling modes. But it's very much the same story as in ADS-CFT. So what I mean by boundary conditions is that, in a sense, there seems to be the analogous thing as some sort of super selection sector, as in ADS, in which you can just select some modes, and maybe it's a consistent way of just looking at those modes without the other modes getting in the way. That's all I mean. So, right, so I was talking about this conformal group, but, well, one curious aspect of this is of course a Euclidean version of the conformal group, but by analogy, this is sort of the very natural thing to consider. Now, this fact that this group, it's really a Euclidean conformal group, has some interesting peculiarities. So, for example, one thing we can say, so going along this line, one thing we can say is that this observer is sort of like a godlike observer, right? So, in the following sense, because correlation functions are Euclidean, there's no way really to compare your measurements there. I mean, you really need to know what's going on there on the whole of square plus. There's no way for you to compare correlations if you are just an observer. In that sense, it's called. I mean, I'm calling it a meta observer. So this is sort of a confusing feature of it, which we would like to understand a little bit more. So related to this, when you go through the machinery of the SCFT, you'll find imaginary weights, which again in a Euclidean theory, so let's say imaginary weights, and again because the theory is Euclidean, there's nothing a priori wrong with this, but again it might be a little bit confusing. One thing that we like in ADS-CFT is that unitarity in the bulk actually translates to unitarity in the CFT. We know what the time evolution is doing, but here, if we imagine we have some theory that has some unitary time evolution in the Sitter spacetime, it's a little bit less clear how to map that to our a dual field theory. What happens to unitarity as you go down to square plus? If we want to now identify time as some sort of RG flow, it's not clear what the unitarity of time evolution is really telling us. So these are interesting and sort of confusing issues. So what to make of unitarity. And also something that's a little bit, different from ADS-CFT is the fact that the theories are defined on the sphere. The dual field theory lives in a sphere, the sphere is square plus. And because we have this notion that the sitter looks a little bit like a thermal state, there's some horizon, which I'll discuss in a second, and we would like to calculate some entropy. And it's a little bit interesting that the way in which these properties come about, let's say from the SCFT, are a little bit different from the way they appear in ADS-CFT, in the sense that, as I said, that theory lives in the sphere. It's not a theory on a torus, for example, the one that lives at square plus. So it's a little bit different the way the thermal properties arise. And we would, I would like to ask the question whether there's another sort of complementary picture to this that we can discuss. So another question that you can ask is, what about the landscape? So what about the landscape? So this is connected with the story about setting boundary conditions square plus, and you would imagine that maybe the issue of the entropy in the sitter requires of us that we consider this landscape of solutions that are hiding, let's say, behind the horizon, and which we don't have access to. By setting some boundary conditions, we're selecting some asymptotically the sitter spacetime, and it's not clear how to deal with this problem, whether this is an issue or not, or if it's not, why is it not? So these are all sort of interesting questions that we need to sort of face by the fact that we're dealing with this theory that lives behind the horizon. So another way of saying this is that this sort of theory is a little bit like understanding. It's a little bit like understanding the black hole singularity in ADS. So the type of theory that lives at square plus is a little bit like the type of theory that you would need to study if you wanted to resolve the singularity that's hiding behind the horizon in ADS. So basically what I'm saying is that, so this is the sitter, so this is a cosmological horizon, And basically, by studying a theory that lives here, it's a little bit like in the sitter studying the singularity behind the horizon. Here, it doesn't matter whether it's a singularity or not, but the question remains that one is faced with this issue about this UV degrees of, about these degrees of freedom that are maybe brane degrees of freedom that one needs to understand, or landscape degrees of freedom in this case that one might need to understand. But it's a little bit like that question. And even though in some particular cases in ADS-CFT we know how to address this question, in the most generic cases, one thing that has proven useful is to understand, for example, where the entropy arises in ADS-CFT from some thermal field theory perspective. So we understand the entropy in ADS, for example, by counting some field theory degrees of freedom in a thermal field theory. So I would like to show you now this complementary picture, and here complementary actually might mean more than just the colloquial sense of the word. I mean, it's really maybe complementarity at work. That now we want to study a different perspective instead of the square plus perspective, but the perspective of a world line observer. So the alternative is the world line observer. So this world line observer. So let me just make this picture. Show this again. Lives here. So let's call this the North Pole, and this is South Pole of the sitter. Because I'm from Argentina originally, I'll decide my observer lives in the South Pole, which is the center of all things. And so one would like to study the space-time from the point of view of this observer, who's living outside the cosmological horizon in some sense. So what I want to argue now is that this observer also has some things in common with the ADS-CFT perspective. So ADS-CFT sort of is mixing things that are happening from these 2 points of view. So let me give you some list of characteristics of this observer and why we might be worried that this observer is a little bit problematic. So one thing that this observer does is it breaks the symmetry. So it breaks the symmetry. And the problem with this, so basically it's breaking the sitter group into this. So whenever you see a D in the blackboard, I'm talking about the sitter in D+1 dimensions. So D is the number of space dimensions in the sitter. So the sitter group which is a isometry group of the space-time given by this. But by choosing the static patch, so this observer only has access to this static patch. So this I'll write the metric in a second. This will become clear. This observer is breaking the symmetries in this sense. By putting an observer there, the only symmetries that remain are just time translations, and then this group of rotations on the sphere. So that's a feature which but might be problematic. There's also the issue of boundary conditions. So here we don't have asymptotia to guide us. So it's a little bit funky. The issue of boundary conditions is a little bit problematic. And another way of saying is that maybe there's no super selection sector. So the question is, how do we pick the modes that we're interested in? So how do we consistently turn off modes that we're not interested in? So this is sort of different from ADS-CFT, and these are good reasons why people you might not be interested in this type of observer. So something actually very severe, which is actually the elephant in the room, is that this sort of breaks gauge invariance. So I'm selecting one particular wall line, and this breaks gauge invariance manifestly. So the question is, how do we live with this? So this breaking of gauge invariance is a little bit what I mean by solipsism. I mean, there's many things you can mean by solipsism. So solipsism just means that we're taking, from some point of view, a conservative approach, which is that we understand that we exist, but we are not sure about everyone else. So from my point of view, all I know is I'm sitting here and I can do do some experiments, but whether you are there or not, I'm not going to worry about this at this point. So gauge invariance means that the observer knows about himself, and he doesn't want to worry about scribe plus and whatever is hiding behind the horizon. He just wants to perform whatever experiment he can perform and see what where that goes. And that's a little bit what this breaking of gauge invariance is doing. And in a sense, you can think of this as complementarity. It's this point of view where you care about what you have access to, and you don't care about everything else. Now, so this is sort of the exact opposite point of view from this godlike observer in some way.
The opposite point of view what we care about mostly in physics.
Sorry?
Isn't it the opposite point of view what we care about mostly in physics, that we shouldn't have things that depend upon our particular choice of observer, and all observers are equal?
Well, okay, good.
Some are more equal than others.
Good. So no, I mean that's fair. So the question, I mean, I'm not going to answer this question today. I mean, it's a complicated question, and I mean, I really don't have a good answer to this. But I mean, the question is whether, I mean, we don't know what the theory of quantum gravity is. We don't know whether there's a consistent theory of quantum gravity in the Sitter space that has gauge invariant observables, and I mean we don't know what is the question we are asking yet, I think. And the question is, if I gave you a box, a black box with a theory of quantum gravity, that would let you ask questions that are sort of gauge covariant in some sense, that require you to decide on a gauge, and then maybe you can talk about other observers, but it requires of you to pick an observer before you ask a question. Maybe that's as good as having some more gauge invariant where you never talk about the observer.
Well, we would say here that all observers are equal because all observers have a static patch and all.
Exactly. So that.
What we wouldn't say is that, and what we never say is that all collections of observers are equal. And in particular, I mean, I think the way we would say it is that we shouldn't ask questions that don't correspond to some physical measurement.
I agree completely. That's what I mean by
So if you have
covariance.
causally separated observers that can't communicate with one another, we shouldn't be surprised if we get trouble when trying to have a theory of what they will simultaneously measure.
That's right. I agree completely. I mean, this is sort of what I mean by covariance. I mean, maybe it's okay to pick a guy and try to reproduce with some theory what this guy would observe. Now, I don't want to spend too much time on this, even though this is obviously a big issue. But I mean, these are the issues that have led us away from this sort of description into this description. But so there are these issues for sure, and in some way we have to deal with this because our current DS phase is represented by this type of observer. I mean, if we look at the inflation, we're looking at the universe from this point of view. But if we're performing some experiment now in our current de Sitter phase, I mean, we're this sort of guys. So we have to deal with it. I mean, we can certainly make measurements and do physics, and we need to understand a way in which we can do physics this way. I mean, at least semi-classically. So this is fine. So another issue, I mentioned the breaking of the symmetry. So the reduced symmetry might help. So again, I don't want to spend too much time on this. So this might help. So people have already discussed that this might actually be a good feature. So actually, in particular, Eric Berlin spent some time sort of arguing that because this group is non-compact, and if you want to build some observable that has this unitary, you might be better off by breaking the symmetry to a compact subgroup and then trying to build observables from it. So again, I don't want to spend too much time on it, but it's certainly a feature of this observer that's breaking the symmetry. So now that we said all of this, so these are sort of some features of this the static patch. Now there's a cosmological horizon. So there's a cosmological horizon. The question that comes to mind is, can we use ADS-CFT? I mean, by this I mean ADS-CFT inspired machinery. So the question is, how do we use that horizon in some sort of ADS-CFT-like context, the same way we use the black hole horizon in ADS-CFT. And for example, another related question is, can we obtain the entropy or the thermal features of this gravitational background by, again, some sort of thermal field theory computation, the same way we do in ADS-CFT? Because now this observer is just standing outside the horizon and he sees this thermal bath, and the question is, can we, in the same way we use ADS-CFT, describe that in thermal field theory language? So that's sort of what I want to say about this observer. So what's the plan for today? The plan for today is to proceed in the following way. Let's impose outgoing boundary conditions at horizon. So this is exactly like in ADS-CFT. So like in ADS-CFT. So there's a horizon. So what I'm going to do is, I don't want to complicate the state this observer is in. So I'm going to isolate everything that happens inside. Notice that this might be different from the type of boundary conditions that you would get by imposing some Banach-Davis vacuum or something where there could be things coming into your patch. But this is not what I'm studying today. This guy is solipsistic. He doesn't believe anything else outside where he is exists, and he's going to make measurements that connect to him. So I'm going to impose outgoing boundary conditions at the horizon, and this is exactly the same thing that we do in ADS-CFT to get thermal field theory correlators. So I'm going to do this. And then what I'm going to do is I'm going to calculate / define world line correlators. Again, the same way we do in ADS-CFT. So this is the plan, as in ADS-CFT.
Your boundary conditions are at the future horizon
It's outgoing.
and the past horizon?
It's outgoing, right? Everything is just things just go out, they don't come in. I mean, it's just one set of boundary conditions, not two, right? So you can regularize the horizon by standing at a very large distance. So it's just one slice, and it's just things go out, they cannot come in. It's exactly the same thing we'll do in ADS-CFT if you had a black hole, right? You just impose that the only modes that you're allowed are the modes that have they just flow out, they don't flow in.
Looks odd though from this picture.
Sorry?
Looks odd from this picture on the past horizon that
It's sort of,
you're not influenced by anything scry minus. Is that?
that's right. So that's what solipsistic means. I mean, you can change that. You can calculate other correlation functions which amount to computing them in some different vacuum. So this is just one particular choice, which I agree might look weird from a cosmological point of view, but things are what they are, and I mean all I care about is that I see a horizon, and whether some other guy coming at me is going to kick me in a second, I mean I'm not going to worry about that for a second. I'm going to worry about what I can do, not what other observers can do. This can be changed. You can change the boundary condition to something else, but again I'm following the most similar road to ADS-CFT. So, good. So that's what I'm going to do. And what am I going to find? So let me spoil the punchline so you don't get bored. I'm going to find a hidden conformal structure. So by hidden, I mean that this spacetime does not have the symmetries of the conformal structure I'm going to discuss. The spacetime has these symmetries. It has just r times rotations, so there's no conformal group anywhere there. But I'm still going to find that the correlation function that I'm interested in transform under some representation of SL2R. Yes?
Does an outgoing mean in this case that nothing crosses the past horizon? Because if you're this particular observer, you cannot. I mean, no light ray can cross the past horizon anyway.
That's right. So that's what I mean by outgoing.
Yeah. So you don't have any.
There's nothing coming from the past.
Is that the same as saying you're in the Euclidean vacuum?
No, it's not. I think. It's not. So, yeah, it's not.
Euclidean vacuum is saying that there's no incoming modes in planar coordinates on the past horizon.
I think it's some sort of analytic continuation of that. I mean, the usual Bunch-Davies vacuum would have stuff flowing for the horizon. That's true. So, yeah, as I said, all I'm going to do is I'm going to isolate the experiments that I can do. So, from a cartoon point of view, you're just sending a guy with a flashlight into the sitter, and you're asking to, turn on his flashlight and see whatever comes back. So he's interested in what he can do, not what comes from the past. Again, this can be changed if one is interested in other correlation functions, but let's look at this one for a second. So as I said, this spacetime does not have a conformal isometry, but still I'm going to find some conformal structure, and we'll see that in a second. And hopefully I can make some contact with the SDFT.
So when you say you'll find the conformal structure, is it only in the correlators that you calculate, or you can argue more generally?
More generally than what?
That is whatever you.
I'll try to explain why this conformal structure arises, but I mean it shows up in the correlators. I don't know what other observables to calculate at this point.
But most general correlator will have this.
We don't know. I'll show you the kind of correlates that we calculate, and I'll show you where the symmetries come from, and then we can talk about that. So
you said you find SL2R, you find world line conformal invariance.
depends on what you do. You might find one or two SL2Rs, but yes. So it's a world line conformal symmetry. Yes. Good. So that's for you to take home, even if you get bored or fall asleep or I fall asleep.
Should I think of this as doing a gauge fixed calculation, but recovering gauge symmetry at the end of the day?
What do you mean gauge symmetry? I mean, I'm picking an observer. I'm going to do this world line. You're asking what's a way to do this world line calculator in a more proper sense?
I'm just saying morally, is this analogous to fixing a gauge, doing a calculation, and seeing at the end of the day that it didn't matter. Everything was gauge invariant.
Why do you say it didn't matter in the end? I mean, another observer might see something different, but it's sort of gauge covariant. We know how to translate what this guy sees to what some other guy sees.
So
right?
I'm just trying to get a sense of why I should.
I mean, this world line sits at some point that's not the origin of some other guy, right? It's not that it's not SOD invariant for some other observer, right? So, I mean, there's a way in which you can map what one observer sees, what another observer might see.
So I was just trying to get a sense of why I should be surprised about finding a hidden conformal structure.
The conformal structure is not part of the de Sitter group.
Oh, I see. It's not.
It's not part of the de Sitter group. It's not part of his symmetries.
Okay.
Good. So, I mean, not obviously at least. So,
Diego?
yes.
Are these correlators, if you double analytically continue, are you going to get the ADS result?
What do you mean by the ADS result? This is a one-dimensional theory.
Well, I'm saying that there were issues in old DSCFT with some of the correlation functions that were computed. If you did a simple double analytic continuation, you would not recover the ADS case. I'm just wondering what.
It's not the same thing. These are different correlators. Okay, so before I get more questions about this, let me actually tell you what the result is. So let's see. So I'm obviously not going to get to talk about everything, so I'll try to run at some points, and if I go too fast, let me know. So, okay, good. So we're calculating this correlator, so let me define what I mean by that. So first, let me just write the static patch metric. So this is the static patch. So this is just given by metric looks like this. So it's something that looks like this, and f is just some function that's given by. So this is a Sitter scale. So whenever you see an L, it's a Sitter scale. So the horizon is at r equals L, and our observer is at r equals 0. So So this is r equals 0, and this is r equals L. Very good. And now, as a warm-up from what I'm going to do, and actually this is going to be enough for our purposes today, let me write down the wave equation, the scalar wave equation in this space-time. So if you do that, you get something like this. So this is a scalar wave equation in the situ space. So the only thing that I introduced here is this thing L. The big L is just the angular momentum on the sphere. So I just reduced, I just diagonalized the modes on the sphere. So this is just a one-dimensional equation now, and I also diagonalized in time. So also let me define in the rest of the talk. I'm going to use this parameterization. So x is just defined this way. So it's another way of talking about the mass of the scalar field. So I won't talk about mass, I'll talk about x. So the thing you should notice is that x goes in this range. So if you pick x in this range, these are what are called the light modes of the sitter. And in the SEFT, they would give you the real weights in the dual field theory. But this is not. This doesn't cover the whole regime of masses, so you can also pick x to be some arbitrary imaginary thing, and these are called the heavy states in the sitter. And if you go through the machinery of the SCFT, these guys will give you the imaginary weights in the dual CFT. So there are sort of two types of modes, whether x is real or imaginary.
So it's interesting that in the one example we understand these imaginary weights don't appear.
What example?
The higher spin.
Oh, yes, of course, yes. I think the reason is that currents are always morally, the lowest possible states with some spin, and so they are always morally light states. The same way, for example, the graviton is a light state. But I agree that it's curious that we don't have to deal with these guys. So one thing I want you to notice is that this metric is a little bit like what's going on in ADS5 x S5 with the S5. So the S5 is sort of an emergent dimension from the point of view of ADS-CFT. It's not in the field theory. It's just something that appears an emergent way. So if you look at this metric, so let's look at the sitter static patch. So near r equals 0. So this is near r equals 0. This thing goes like minus dt squared plus r squared. I'm just looking at the sphere. I don't care about the radial part for a second. So this is just something like this. And in ADS5 cos S5, just to give you a particular example, this thing goes like so the r is in a different place. These metrics are sort of conformally related. But the point is that from the point of view of the observer at the boundary of ADS5, the sphere is actually very small near the boundary. So compared to his time lapses, the distance in the sphere are very small near r equals 0. And this is the exact same thing that happened from our de Sitter observer. So near the world line, the sphere that sits around him is very small. So we should think of this sphere in de Sitter as some emergent space directions, the same way the S5 appears sort of in ADS5 cross S5. So that's why there's a conformal quantum mechanics sort of lying at the bottom of the story, because the extra dimensions will always be emergent. So I mean, it's just an analogy. You don't have to take that too seriously. So let's see. So having done all that, let me define the correlators. So, oh, actually, before I do that, which I'll do in a second, let me talk about gravitons for a second. So you can decompose a spin-2 field under the SOD symmetry, and it turns out that you have a scalar mode, a vector mode, and a tensor mode. And each one of these modes actually satisfies the exact same equation that the scalar field satisfies if you pick the right x. So for the scalar mode, x is given by, so this is a graviton. So for the scalar mode, x is given by the absolute value of d minus 4 over 2. The vector mode is d minus 2 over 2. And the tensor mode is just d over 2. So if you pick the right x's, this is actually the same equation that governs the graviton perturbations. For a reference, the conformally coupled scalar, so conformally coupled scalar, also satisfies the same equation. It's just a matter of picking the right mass, and x is 1/2. So what I want to argue from this numerology is that d equals 3 is special. So so d equals 3 means ds4, right? So it's us. So d equals 3 is special. If you go through these numbers, you'll see that for d equals 3, this is 1/2, this is 1/2. So some sort of miracle happened, and both modes have actually the same mass, and actually they have the same mass as the conformally coupled scalar, and this guy is not there. So in 4 dimensions, there's no tensor mode. There's not enough space-time dimensions to turn on this mode. So what I'm showing you is that the dynamics of the gravity under this decomposition in the cytostatic patch is exactly the same as the dynamics of a conformally coupled scalar, at least at the linearized perturbation level. So this is very interesting, and it'll play an important role. And maybe there's a connection between this and this whole story about conformal gravity in 4 dimensions. So again, I don't want to spend too much time on this, but d equals 3 will be special, and will be different from the other cases. So now let's move on to actually write down the correlations. So basically what we're going to do is we're going to write down the solutions to this equation the following way. Some coefficient times a non-normalizable mode plus some other coefficient times a normalizable mode. Let me tell you what I mean by this. So let me actually write the solution. So the normalizable mode goes like this. So I've already imposed outgoing boundary conditions. So that's the normalizable mode, and the non-normalizable mode, very similar. That has a different power here. And some hypergeometric function. So what I call this one the normalizable mode, because as long as you turn on the angular momentum, then this guy decays at the origin. So if we're sitting at r equals 0, this mode just vanishes there, while this mode diverges there. So it's again very similar to what happens in the DCFT story. This is a mode that's small, and this is a mode that diverges near the origin. So now we would like to define a correlation function. Oh, I haven't told you what these coefficients are. There are some b's that appear here. A's and b's are just functions of omega and L that are not very important here. So let's not focus on those guys. And h plus minus are numbers. Let me write them. Are given by this. So this one has like b plus h minus, b plus h plus, more stuff. So a and b are just numbers, but these guys are sort of important, and they're given by that. So now let's define the correlation function. So we can be very, very naive and do the exact same thing that has worked many times in ADS-CFT. So we have a recipe on the way we do this in, let's say, finite temperature ADS-CFT. What we do is we just define the Green's function to be, so the Green's function of omega. We just define this to be, let's say, B over A. So it's just a quotient of the normalizable mode to the non-normalizable mode. This was a little bit fast, but if you do it properly and you define the Green's function in the bulk by using the Wronskian and you do the whole thing, you will get the same results. So you can trust that this recipe actually works. So this is just a shortcut to get it. So this exact same thing that we did in ADS-CFT, and if you calculate this, you get the following result. You get a product of two functions of omega, and let me write what these functions are. Actually, even before I write all of this, once you've seen some hypergeometric functions arising, you start suspecting SL2R, conformal invariance, blah, blah, blah. And this sort of, actually, the story where Andy was involved, where in Kerr CFT, these sort of structures also have appeared. But let me just point out that these hypergeometric functions really are appearing for all omegas. There's no low energy limit involved. So this, I haven't taken a limit to get that. So these functions p plus and p minus are given by this in gamma functions. And it's a product of these two guys, one with a plus sign and the other one with a minus sign. So before I explain this in more detail, let me point out that if you now pick x equals 1/2, which corresponds to the DS4, something actually special happens, and this product of two functions actually coalesce into a single gamma function. So in general, you will have two gamma functions on the numerator. And for this particular case, they coalesce and they make just one gamma function. So in that particular case, this thing is given by something that looks like so it's just one of them. So this is what happens when you pick x equals 1/2. Very good.
Are these quasi-normal modes? No.
Good. No, these are not, but the poles will be quasi-normal modes. So
Poles of what?
the poles of this Green's function. So let me get to that. So now, before I'll talk about the poles in just a second, but let me just point out that if you're not familiar with these gamma functions, you can Fourier transform this expression, let's say this one, so for x equals 1/2, and you can see what you get, and it's actually very simple. You will get the following result. So x equals 1/2, you will get, it's a retarded Green's function, so you get a theta function in front, but
This is the Green function just at the South Pole?
This is a yes, there's no mixed correlation function. This is a correlation function from exciting something at the South Pole and then getting the response back at the South Pole. And this looks like this. So, if you're familiar with conformal quantum mechanics, you'll notice that this correlation function is just a correlation function of conformal quantum mechanics and the time evolution with respect to some particular direction. Another thing you can see is that this correlation function is periodic in Euclidean time. So this is actually the correlation function of some quantum mechanics at finite temperature, which is exactly what we were expecting to get in the Sitter space. So it's actually very simple. And this sort of thing is just telling us what the weight of our operator is. So this all hints to conformal quantum mechanics. And
wait, we could have written that expression down immediately just from the fact that the Sitter space analytically continues to the fourth sphere, right? And therefore it must be periodically.
I don't think so. These correlation functions are not natural on the sphere, right? I mean, I'm calculating world line correlators, not. So, I'm not sure that's.
If you take t to it, you're in the Euclidean vacuum, so it must.
Again, this is at r equals 0, right? So these are correlation functions calculate some point on the sphere with itself. As I said, these symmetries are not the symmetries of the de Sitter spacetime, the ones that give you this structure. So let me try to get to what they are.
What was L again?
The capital L is the angular momentum under the SO, is a Casimir under the SOD. So I've decomposed the modes under the symmetries, which are R and just time translations, and rotations under SOD. So that's omega and L. We can talk about this later. I don't think so, but maybe there is a way to get them from the sphere. So very good. So we were talking about quasi-normal modes. So let me write what they are. So let me write them like this. So it's just a collection of omega n's. Let me put the L here. It's just the de Sitter scale. And it turns out that because there's two functions, p plus and p minus, that these guys have, each one has its own family of poles. So let's write both of them. So there's two of them. There's the plus and the minus guys. And they are given by this expression. So again, this is hinting to more conformal symmetry. This is a spectrum of equally spaced modes. And there's just two of them, and it's like each one has its own weight, and each one has an infinite tower of equally spaced modes on top of them. Now, in particular, in x equals 1/2, as we were arguing there, these two families of poles coalesce. So the poles here are given by, let's say, some delta minus and some delta plus here, and then they are equally spaced on top of them, and here they start mixing, right? The ones that come from one or the other start mixing here. But this is what the structure looks like. But if we pick now x equals 1/2, something special happened. These two families of poles sort of get one on top of each other, and well, let me just write what you get. So for x equals 1/2, you get so the spacing used to be 2, but now once they are on top of each other, the spacing becomes 1. So it's like 1 is exactly 1/2 offset of the other, and then the two families of poles just become one single family of equally spaced poles. So actually it's very similar to what happens in the harmonic oscillator. If you solve the harmonic oscillator problem, let's say if you solve a conformal quantum mechanics problem with a coupling, you'll see that the equation of motion for the harmonic oscillator will just give you the value of the Casimir, and there are two solutions for the value of the Casimir. They are two values that depend on the coupling constant, and I actually, maybe I don't have time to go through this, but so as an aside, so in a harmonic oscillator with some coupling, so it's a Hamiltonian that looks like so it's some conformal coupling. You can calculate the equation of motion will give you the Casimir, and the Casimir will be given by something like this. So there are two representations in principle, because there are two solutions to this quadratic equation, because the Casimir is a quadratic operator. And what you will get is that in particular, if G equals 0, so C is the same as delta minus 1, and you will get that delta is 3/4 and 1/4. So the two solutions to this equation become this, and as you can see, they are offset by just a half. So the spectrum of the harmonic oscillator was in principle for a generic coupling given by two families of modes, and it's just in a particular case where G equals 0, so you have exactly a particle with no conformal coupling, that you will get the spectrum of the harmonic oscillator. So there's actually some interesting story with the way this algebra is realized, but I don't have time to talk about it, so let me skip over it. Right. So, and it turns out you can, so going back to our equation, it turns out you can write some differential operators that act on these modes, and they realize the SL2R algebra. So if you look at that formula for x equals a half, you can act with some differential operators on top of these solutions, and there's some representation of SL2R that maps one type of solutions to the other ones. So again, let me, in the interest of time, let me just skip over most of this, but let me just say that there are H plus, H minus, and H naught differential operators that look like, dt plus dr plus stuff like that. And when you act with these guys on those quasi-normal modes, they map the one type of quasi-normal mode to the other. So they are in a representation of SL2R given by these guys. So these guys give you an SL2R. So, right. So where does the SL2R come from? So let's look at this case before I get to the more generic case. The SL2R comes from this fact. dsd plus 1, so this is the metric of the sitter. It's actually, so no square, I'm sorry. So the sitter in d plus 1 dimensions is actually conformally connected to ADS2 times SD minus 1. So these two spaces are actually conformal to each other. There's a value scaling you can do in the metric, and these two spaces are connected. So in 3 dimensions, in 3 spatial dimensions, the dynamics of the graviton is just the dynamics of a conformally coupled scalar. And the conformally coupled scalar cannot see the Weyl structure in front of the metric. So that's why in the sitter 4, the fact that these two spaces are conformally related guarantees that the correlation functions of the graviton are just given by the same correlation function that you will have calculated in this spacetime. And this spacetime has an SL2R. So this SL2R is conformally killing vectors. They're not killing vectors, but they're conformal killing vectors of this metric. It's interesting that under this mapping, if you pick a wedge of ADS2 such as to make an ADS2 black hole, the horizon of the cosmological horizon maps to the horizon in ADS2, and the observer maps to the boundary of ADS2. So under this map, we're really calculating boundary correlators in ADS the same way we are used to doing. So this is actually the same result you would have gotten from ADS CFT, as I said, in DS4. So just to finish with this case, let me just point out that these quasi-normal modes for generic X, so when they have these two different types of modes, actually if you continue the solution past the horizon, you can do that, and you can see that they actually match exactly to the slow decaying and the fast decaying modes that Andy has studied in NDS-EFT. And actually then you can calculate what the weight is that comes from this formula, and this matches the weights that you can see in DSEFT. So there's a formula for this guy given by d plus minus equals h plus minus plus L over 2, and this formula matches the story in the SCFT. So in a sense, this view on the quasi-normal modes in the static patch is sort of a complementary view to the fast falling and slow falling modes.
What are the things that match here?
So if you grab a solution that's a quasi-normal mode, and you continue it past the horizon, you continue it for R greater than L, these are the fast falling and the slow falling modes that you studied in Scribe Plus. And
everything is a fast falling or a slow falling. Wait, you're saying some kinds of quasi-norms?
They could have been mixed, right? But they're not. The quasi-normal modes are exactly those modes. So these correlation functions that we're calculating are sort of a complementary dual to.
But they have contributions from both kinds of quasi-normal modes. Right?
Yes. Sort of this duality is between quasi-normal modes and Euclidean correlation functions. It's not between our correlation functions. There's a change of roles between the physical modes and the quasi-normal modes. Yes?
What would happen if you consider dynamics in spacetime where they are only asymptotically DS? It's like that I presume that this sort of conformal relation would not be true in general.
itself outgoing modes?
No, I mean, if you just consider dynamics in spacetime, which are not ds, but
Oh, of course,
totally ds,
of course,
then this.
of course, this is not true.
No, so even the wave I mean, it's an accident of the wave operator that at x equals half. I mean that it, but it wouldn't be true for the nonlinear.
Well,
That's right.
well, that's an interesting question, and
Generically, you wouldn't expect.
well, maybe with the right boundary conditions, it could be, right? Again, we know that, for example, in 4 dimensions, there are ways to make Einstein gravity look like conformal gravity. So
Well, but
maybe. All I'm going to talk about here is at the linear level. And it's, of course, a very interesting question to see what you can do beyond the linear level. But
whether this conformal structure really persists beyond 2-point function.
that's an interesting question, and I don't have an answer now. But at least in 4 dimensions, you might hope that this is a way to make it work. So, and maybe again, maybe in other dimensions as well. The way the symmetry appears in other dimensions is actually a little bit different. It's a little bit more complicated, and let me just be very brief about it. So, this argument that I just gave you works for ds4 because I used x equals a half, and I got the ADS2, and I did everything that using that. But we saw that there is this conformal structure, these 2 families of poles that appears nonetheless. So this p plus and p minus, each one they give you things that come from a conformally coupled from a conformal theory. So the question is how you can get them in general. So there are various ways to see this. One way to see this is to make a change of variables on the scalar equation that I just solved there. And it turns out that, again, I'm going to be brief. So by picking the right variables and really finding your field, you can write this equation as the Poisson-Teller equation. So there's a way to rewrite this equation as the Poisson-Teller equation. The Poisson-Teller equation is just an equation that looks like this. So this is the equation that you get. And it turns out, so as I show you, there are 2 families of modes, two different families of Gaussian modes. And the Green's function actually factorizes into these 2 pieces. And what you can see is that if you actually solve the wave equation, again, in the right variables, in ADS3, this is exactly the same equation of a scalar in ADS3. So the way this happened is the following. So again, in the right coordinates. So the way this happened is the following. So what is true is the following statement. So if you add a direction, so basically this is the equation of motion in ADS3, where x is the momentum on one of the directions, and omega is the energy. So this momentum actually corresponds to something else. So what's true is that de Sitter in d plus 1 dimension times a line, so I'm just adding a line by hand, times a line, is conformal to ADS3 plus st minus 1. Now, any mode, again, this is at the linearized level, any mode in de Sitter d plus 1 with any mass can be thought as a kk reduction of a conformally coupled scalar in this larger spacetime. So because of this reason, it doesn't matter what the mass of your field was, it does satisfy the symmetries of this mapping, because the conformally coupled scalar, again, that cannot tell the difference between these 2 metrics, so it's experiencing this symmetry is given by this spacetime. And this spacetime has SL2R cross SL2R, so there are 2 SL2Rs going on. So you can actually use the symmetries to obtain the correlation function from scratch without doing any calculation, just using the symmetries. And you can actually show that the Green's function in that case is given by G. So there's some weight, let's call it like that. So this is exactly the Green's function you will get in a 2-dimensional CFT. It's just a left moving and a right moving part of the Green's function. One depends on a left moving frequency, the other one on a right moving frequency. It's exactly what you get from ADS3. And the only thing you have to do is to to pick the parameters the right way. So P is given by minus Ix. So you're forced to pick P to be something. P is not a free parameter anymore. So one way of thinking about this is it's like a level matching condition. The same thing we do in string theory when we think of string theory in the wall sheet as a two-dimensional CFT, and then we impose a condition on the spectrum that the two SL2Rs were not really independent. So this is the exact same thing. We have two SL2Rs, and at the end of the day, we're truncating the spectrum by deciding that the momentum operator is actually connected and it has to be some value. And then this thing is by something that's so what's interesting is that for example this works for any operator, for any x, and the curious fact is that in this theory, which is Lorentzian, we managed to get conformal weights that are always real, even though some of these modes would have had imaginary weights in the dual Euclidean theory according to the SCFT. So I'm already running over time, so I wanted to tell you a little bit about the conformal quantum mechanics interpretation of this story, but I guess they'll have to wait. I can discuss that privately if you're interested in this. The take-home message is that there is this conformal structure that we didn't expect to find. Whether this extends beyond linear level or not is a very important question, and that's an interesting direction. Possible directions out of this, some of these directions we're pursuing is, for example, one thing is that we would like to find a conformal quantum mechanics that at large n reproduces actually the dynamics of the Sitter spacetime. And actually, that's not so hard to do. We might actually be close. And actually, if you consider free theory of just n particles of conformally coupled, they actually are very, very close to giving the right results. So it's actually not that far-fetched. Another direction is trying to exploit the fact that you have this ADF3 structure. So notice that for the sitter in any dimension, there is this ADF3, this 2SL2R structure. So it doesn't matter what dimension you're in, you always get ADF3. So one way to push this further, and I don't know if this will work or not, is to try to understand whether one can try to obtain the entropy of the sitter by doing some ADF3 calculation where we know how to do this by using the central charge. And lastly, let me just point out that one other thing that one might do is we might try to have a particular brane construction of this story and see if this is something we can actually do. So actually, Eva Silverstein and collaborators, they have actually uplifted some ADS4 solutions to DS4, and in that case, they know how to do brane counting of the degrees of freedom and get some matching with the entropy of the sitter. Now, you could now hope to be able to do something similar in this case if you were uplifting some ADS2 cross S2 vacuum to DS4, let's say. And there you will be counting degrees of freedom in some line, in some wall line theory instead of in a field theory. And well, these are all future directions, so let me just leave it here. Thank you very much.
Questions?
Yes?
So this Green's function, which is sitting on the top there, is kind of problematic because that, of course, is the Green's function for something interacting, in the presence of a heat reservoir with an infinite heat capacity. And we might think that it's an exactly thermal Green's function.
Yes.
And so we might think that de Sitter space is not an infinite heat reservoir.
You worry about recurrences?
Yeah, so we should expect to see recurrences and other kinds of non-perturbative corrections to the...
You should think of this as a large n result, and
as a large n result.
But I agree completely with you.
So
One would expect that.
We would not want to find a dual quantum mechanics that reproduces this exactly.
Well,
it should have some kind of non-perturbative corrections, I think. I'm not sure the right way to think about it, but
I guess you would
certainly
say
once you write down that formula for the Green function, you're in trouble.
the way thermality comes, the way thermality comes about in a conformal quantum mechanics is a little bit naive, right? Because you can start with some quantum mechanics and some non-thermal vacuum and calculate correlation functions and go like powers of t's. And then thermality just appears by changing what you mean by the time evolution. You're just doing time evolution with respect to some other operator. And so you know, in 0 plus 1 dimension, thermality, that doesn't mean much. So so I don't know if there's a way to fix that. I'm just saying that thermality is a little bit less
I mean,
mean.
if you're sitting at the South Pole and you can really measure your green function exactly, you can.
Oh, of course,
You
of
can
course,
determine whether
of course. But what I'm saying is that
the heat capacity of the reservoir that you.
of course. What I'm saying is that the difference between a vacuum correlation function and a thermal correlation function 0 plus 1, it's a little bit vague because it's just changing the time evolution. It's just deciding you're evolving along some other direction. Instead of picking some h to be your time evolution, you're just picking h minus k in this case to be your time evolution. So, but I sympathize with all your concerns, though. I'm just saying in 0 plus 1, maybe there's some way around this.
Any other questions? I have a small question. So, this conformal structure that you brought out, was it really a property of de Sitter or was it a property of horizons? The reason why I ask that is, you know, you had this whole thing with the neck and so on, and then you did some discussion calculation, it was a conformal structure there. And here again, you're doing some sort of something.
So it's a question of whether you need a low frequency limit or not. So you would expect that maybe in a low frequency limit, this has a little bit to do with physics horizons, and maybe Andy can expand on that. But people have found this structure in Schwarzschild black holes, right? For example. But the curious thing about this geometry is that this geometry has this structure for all bodies of the frequency. So you can extend this conformal structure all the way to the UV, all the way to the observer. The low frequency limit of this might be connected with the existing.
We found a conformal structure that's reminiscent of this for black holes even far from extremality. So it had nothing to do with neck.
Right.
But exactly. There's a conformal structure.
It was a conformal structure in the absence of any conformal killing vectors, and this is similar in that way.
That was what I had in mind.
This SL2R is not a subgroup of the SOD common one.
Yeah.
Okay, let's thank speaker again.
Thank you very much.